Assalamu alaikum. Welcome to the sixth lecture in the facts. In the previous lectures, we discussed about the shunt and the series compensation. Today, we'll discuss about the phase angle control. So, as we know, we have uh, we have to control this impedance. We have to control the voltage. We have to control the delta. So, usually, shunt controllers are used to control voltage. Series controllers are used to control the series impedance, and phase angle control is used to control the delta. So here you can see over here that this phase angle control is used to control the load angle delta. Sometimes in practical power system, it may happen that the angle delta required for the optimal use of line may be incompatible with the overall operation of the line. That means we may have delta which is greater than usually 10 degrees, 20 degrees or 30 degrees, because we always want delta to be very small. So sometimes this delta is very close to 90 degrees, it may be incompatible because it may not be stable transit in transient nature. So this may happen when the lines are connected by the multiple links of different lengths when the two buses are intertied whose prevailing angle difference is insufficient. So when the two buses are tied, connected to each other, and they have the two lines which are of different lengths, there is a chance that this angle is again very insufficient. So in that case, what is done? A phase shifter is introduced like this in series with the line or in series with the voltage source, so that the voltage that is seen by this receiving end, now the sending end new or effective voltage will be equal to Vs plus this V sigma, that is the voltage that is injected in series with this Vs. So in the two machine model, here a phase shifter is introduced between the sending end and the receiving end, but it is usually connected at the receiving end. So the phase shifter usually is a sinusoidal voltage source. It has a controllable magnitude and phase angle, both controllable magnitude and phase angle. So the effective sending end voltage will be Vs effective will be equal to Vs plus V sigma. So it is evident from this figure. This Vs effective will be equal to this voltage plus this voltage. So when we do this, this Vs effective is equal to Vs plus V sigma. This is, as I have told you, that the phase angle is the angle between this voltage phasor and this. This will be now the phase angle, and this magnitude will determine this sigma. If this magnitude is more, the sigma is more. This magnitude is less, the sigma is less. So depending upon this value, this is the actual value of the angle that is between Vs and Vr, that is delta. Now this angle between Vs effective and this Vr will be equal to delta minus sigma. So here this V sigma is introduced in such a way so that this Vs is equal to magnitude of Vs is equal to magnitude of Vs effective is equal to magnitude of Vr. Let us say it is equal to V. That is what I have written here. So then P is equal to, that is the voltage between voltage of this multiplied by voltage of this divided by the reactance, because reactance, you can see all the reactance is between this voltage and this voltage, and the angle, sine of angle between the two. Now the angle between the two is delta minus sigma. You can see from here, as I have told you now, if delta is very large, by introducing the value of positive sigma, this can be reduced, and this power curve in that case will be shifted towards the right. So when delta is reduced, you can see that this transient stability in this case has increased. Even if the steady state stability has not increased, because Pmax is as it is, it does not increase, it remains as it is. If we increase it in such a way so that we increase this value Vs effective as well, in that case there may be chance that this peak will increase and steady state stability will increase. But here we can see that transient stability will increase because this delta will, now the overall angle between this and this will reduce. So for the same value of delta and plus, that's positive sigma, the power transmitted will be less, so that the curve shift will shift towards the right. You can see from here, as this curve is for the positive delta, and then the net angle will be smaller. That means this angle will be delta minus sigma, and this curve will be shifted towards the right. For a particular value of delta, definitely the power will decrease, but the stability will increase. That is the transient. The basic idea behind the phase shifter is to keep the transmitted power of a desired level independent of the existing transmission angle delta. So you can see from here, what would be the case if actually usually we want that in this case the power transmitted should be independent of the delta, because we change the delta in such a way so that power transmitted will be as it is, and by decreasing the delta. Here we only show the power transmitted has decreased, but we can increase the value of this so that power transmitted will remain the same. This peak will increase, but delta will decrease. So in that case, we are keeping the power transmitted same but decreasing the delta. So we are keeping our desired thing same without actually affecting the transient stability. So by keeping the please keep this in mind, by keeping the power transmitted same, decreasing delta, we have to increase the value of the voltage. So in that case, this Vs effective will increase. This may be perpendicular to this. You will see that then Vs effective will be greater than this, or even this may be at an angle which is greater than 90 degree to this. So by having a desired magnitude or phase angle of this V sigma, we can change its angle as well as its magnitude as well as its peak. So that's what this means, that we can make this desired power independent of existing transmission angle delta, and we can operate it in the desired operating range. One more thing, the power can be kept at its peak value even after the delta exceeds pi by 2. So we can kept it at the peak value. That means we can keep delta to be equal to 90 degrees, but overall angle will be 90 minus some sigma depending on the value of the sigma. But you will see that overall angle, which is actually the sufficient angle or the angle that is seen between this V sigma and VR, will be less. Now this is the case when sigma is introduced of negative value. In that case, this power curve will shift towards the left. Now this is the actual diagram. I have actually redrawn it to make you sure. This angle is sigma minus delta, this angle is sigma minus delta by 2. So what I mean to say is that you can see this phasor that is I into x, magnitude of this will be I into x, its half will be ix by 2. It will be equal to cos component of this, sorry, sine component of this, that is VR sine of delta minus sigma by 2 will be equal to ix by 2. So in that case, we'll be able to calculate the value of I. Similarly, for this case, you will see that uh, when we draw a perpendicular from here to here, you can see these two are equal and its midpoint will be the perpendicular bisector. In that case, its half will be equal to Vs effective sine sigma by 2. So actually I need to calculate the rating of this phase shifter. The rating of this phase shifter will be equal to this V sigma into this I. So that is what I have written over here. This VA rating of the phase shifter will be equal to V sigma into I. It will be equal to twice V sine sigma by 2. That's here, because this is equal to V sigma by 2 will be equal to Vs effective sine of sigma by 2. So V sigma will be equal to twice Vs effective sine sigma by 2, but Vs effective is equal to V, that will be equal to twice V sine sigma by 2. That is what I have written here, twice V sine sigma by 2, and I will be equal to twice V sine delta minus sigma, that is delta minus sigma. I have written as delta, please correct it, delta minus sigma by 2 divided by x. So it can be calculated from here, because ix by 2 will be equal to sine delta minus sigma by 2, or I will be equal to twice sine twice V sine delta minus sigma by 2 divided by x. That is what I have written here. So the total will be equal to twice v square by x sine sigma by 2, the magnitude of the voltage. This actually tells us how much will be the magnitude of the voltage, and this will be magnitude of the current that is flowing through the this phase shifter. So this phase shifter is capable handling both active and reactive power. So since it is dependent, we can change its magnitude as well as its phase angle, so it can be used to handle both reactive as well as active power. Now coming back to this, we'll just try to introduce you some definitions, some important definitions, and based on these definitions we'll be explaining them one by one. But first we will define different controllers. So what is the objective of the fact, as I have told you in the first class? So it is used to increase the power transfer capability of the existing transmission system and to keep the power flow over designated routes, control of power flow in the lines. So sometimes we have to change the length of the line by increasing or decreasing the reactance of the line. In that case, we can change the power flow through the lines. So that's what is meant by the power to keep the power flow over the designated routes. So this is achieved by using the high power electronics. So rating of these controllers will be hundreds of MVAs. So facts is actually a combination of power electronics and power system. Power electronic converters are used to control the power system devices. So doing this, we have to ensure certain things. We need to have a proper coordination and overall control of the fact devices to achieve maximum benefit. They should be coordinated and they should be controlled in a proper manner so that maximum benefit may be achieved. And we have to prevent the undesirable things with different system configuration. When we have to introduce such controller, there should not be introduction of the undesirable things that are to be avoided. Now, what is the definition of the facts? We can say this is the facts technology. It is the AC transmission system which incorporates the power electronic based and other static controllers to enhance the controllability and increase the power transfer capability. This is the definition of the facts technology. So what is the facts controller? It is a power electronic based system and other static equipment consisting of other static equipment that provides the control of one or more power system parameters. As I have told you, facts controls are used to control X, V and delta. Usually facts devices are divided into two categories. Actually, they are based or divided on the base of the switches used. The first group is that is the reactive impedance or tap changing transformer. They are basically based on thyristors. So when we change the impedance, whether we have an inductance, whether we have a capacitance or a tap changing transformer, so in these we use the thyristors. We have other, that is self-commutated device based control or GT or IGBT. They are used for high power applications. Actually IGBT and GTU. So in this case, as we know that thyristor is a semi-control switch, we can switch it on, but we are not able to switch it off. It depends upon then the natural commutation or forced commutation. So here we don't have to use the forced commutation. We can use simple gate signal to turn them off. So that's why we are calling them self-commutated devices. Now let us start defining or introducing you some important controllers. Will start from static var compensator. It's also or shortly known as SVC. It is a shunt connected static var generator or absorber, usually connected in shunt, that is between the line and earth, and it can var means reactive power. It can generate, supply the reactive power, or it can absorb the reactive power whose output is adjusted. That means output current, whether it is an inductive current or a capacitive current, to exchange the capacitive or inductive current so as to maintain or control the specific parameter of the transmission system, usually the voltage. So in this case, this capacitive current is adjusted by adjusting the thyristor firing angle. So this output current can be of inductive nature or capacitive nature depending upon the desired thing. If the voltage of the system is more, so in that case it will supply the or it will draw the inductive current. If the system voltage is less, it will draw the capacitive current. So how is it's connected? This is the broad, you can say, typical layout or typical diagram of a static var compensator. It consists of, it is connected usually shunt, that is between line and ground. It is a converter transformer or coupling transformer. It is a step down transformer. So we have a TCR. This is known as thyristor controlled reactor or thyristor switched reactor. So we'll discuss them as well. This is the thyristor switched capacitor. There will be only thyristor switched capacitor. There will be no thyristor controlled capacitor. This is the filter. Because of these power electronic devices, there will be some harmonics introduced, and this filter is used to filter out those harmonics. These are mechanically switched reactor because you will see that it will introduce a fixed value of inductance. This will also use a fixed value of capacitance. So in the coming classes, I will tell you what is the main difference between this and this. So for the time being, you can see the operation of this and this will be quite identical. This can be switched on and off only. It can be there for there when it is on, it will be a maximum value. When it is off, it will not draw any current. Similarly, when this is switched on, it will draw maximum current, and when it is switched off, it will draw zero current. But for this case, when it's a TCR, this current can be controlled from 0 to maximum value depending on the value of firing angle alpha. So actually this is nothing. If you this is not a new circuit. This is actually a AC voltage controller where we have an inductive load. This is also an AC voltage controller where we have a capacitive load. Usually you might have read in your power electronic classes AC voltage regulator with resistive load or RL load, but here we have a purely inductive load and we have purely capacitive load. So for an AC voltage regulator, when we want a controllable current for a purely inductive load, the firing angle should be from, it will always be from 90 degree to 180 degree, and from 0 to 90 degree it will lose its control. It will be as if it is directly connected to this. There will be no control from 0 to 90 degree. The control of current, inductive current in this case, that is for the inductor, it will be from the 90 to 180 degrees. So SEC includes separate equipment for leading and lagging wars. Leading wars we have this and this. For lagging war we have this, that is TCR and MSR. So you can see from here I have written over here, for absorbing reactive power we have TCR or TSR, that is this component, and MSR. I have forgotten to write this as well, but this is also for leading, for absorbing the reactive power. Providing the reactive power we have TSC or MSC. So this is all about, we have static var compensator. So now come to the thyroid control reactor. This is this part of the SVC. So it is again a shunt connected thyroid control reactor or an inductor whose effective reactance is varied in a continuous manner. As I have told you, its reactance can be controlled, or its reactive current can be controlled by the conduction control of the thyristor. But that means by varying the alpha. It is a subset of SVC as we have seen just before, and by controlling the conduction time, that is alpha, current through the reactance can be controlled. This current can be controlled, and this is the firing range for controllable current. As I have told you, please look into that, why we have a controllable range only from 90 to 180 degrees. From 0 to 90 degrees it will not have any control over the current. This current will be continuous, and it will be as if it is directly connected to this inductor from 0 to 90. From 90 degree to 180 degree the current will change. The current will be controlled. The current magnitude will be reduced. Now we have one more thing, that is the thyristor switch reactor. It is known as TSR. So it is again the same thing, but only difference from TSR and TCR is alpha. You'll see that a shunt connected thyristor switched inductor or reactor whose effective reactance is varied in a stepwise manner. In the earlier case it was a continuous manner, and in which alpha was changed from 90 to 180 degree, but here it is a stepwise manner. What are the steps? We will see just by either full or zero conduction. So full conduction will be at alpha is equal to 90 degrees, zero conduction will be at alpha is equal to 180 degrees. So here there will be two values of alpha only, that alpha is equal to 90 degrees and alpha is equal to 180 degrees. That is why it is known as thyristor switch reactor. When thyristor is put on, alpha is equal to 90 degrees, it is switched on. When thyristor is put off, alpha is kept at 180 degrees. So there are only two values of alpha. It is also a subset of SVC. Firing angle is either 90 degree for full conduction or 180 degree for zero conduction. There are actually several inductance placed parallel to get a different values of the reactance. Actually, we get the fine control of the reactances when we have a thyristor switch reactance. In that case, we have a cost less as compared to the thyristor controlled reactance. Similarly, we have a thyristor switched capacitor. It is a shunt connected thyristor switch capacitor whose effective capacitance is varied in a stepwise manner by either full conduction or zero conduction of the thyristor. This is also a subset of SVC. In this case also, we have two values of alpha only. When alpha is equal to 90 degree, this will be put on. Alpha is equal to 180 degree, this will be put off. In between, there will be no value. Again, there will be several TSCs placed parallel to each other, and unlike TSR, shunt capacitance can't be switched continuously without with variable firing control. So as we have thyristor control reactor, we will not be having thyristor control capacitance. We'll discuss this why is not there when we come to this TSC. So for the time being, I think this is enough for today's class. Thank you.